Um, Hello, everyone. Today, I'm going to be presenting our work on modeling attention in human crowds. This is joint work done with Katharina, Muelling, and Gino at Robotics Institute, Carnegie Mellon. In this work, we seek to answer the question, how do we achieve autonomous robot navigation in human crowds? In real life, we typically see crowded scenarios like the one shown here. If we expect mobile robots to play a part in our day-to-day life, we expect them to be able to navigate in these crowds. But before we set out to answer this question, let's do a small exercise. So in this frame, try to guess where the circled pedestrians would move in the next few seconds. As you can see, the pedestrians circled in red are trying to go left. The pedestrian circled in blue is trying to go right. I'll give you a few seconds. As most of you probably guessed, the lone blue pedestrian actually moved out of the way and avoided collision with the incoming red pedestrians. Now, this is very intuitive, and it's a very common behavior for us. If we want robots to have this intelligent behavior, maybe we should first analyze how we as humans do it. While we navigate crowds, we pay attention to important pedestrians around us who might be in our way. We figure this out by first predicting their future trajectories and then following social norms while avoiding collisions. Like in the example that we've seen before, the social norm was to move out of the way for a larger group. This gives us some insights as to how robots should navigate naturally among human crowds. So the goal of robot navigation is safety and interpretability. Safety is ensured by avoiding collisions with other pedestrians, but interpretability is a little tricky to define. Interpretability requires the robot's trajectory to be intuitive to surrounding pedestrians. Or in other words, it should be very human-like. But that's a very challenging problem. The key challenges in achieving human-like social robot navigation is that we need to model human-human interactions within the crowd. This is a complex problem as we need to do a joint trajectory prediction problem which scales exponentially with the number of agents in the crowd. So we need approaches that can scale well with the number of agents in the crowd, but still result in accurate trajectory prediction. Previous work that tackled the same problem include interacting Gaussian processes, which model each trajectory with a Gaussian process and then use the local interaction model on top of it. Other works include using inverse reinforcement learning to recover the cost functions that we as humans try to optimize while navigating a crowd. A more recent work is social LSTM, where you model each trajectory using an LSTM and then use a spatially local interaction model on top of it to capture these human-human interactions. But as you can clearly see, that all of these works are restricted to local interactions. That is, they make an assumption that the human-human interactions within the crowd are spatially local, which is not necessarily true. For example, consider you walking down a hallway, and there's a pedestrian who's far down the hallway who's coming towards you. If this pedestrian is moving really slow, you wouldn't be paying attention to him. He's not really useful for your current trajectory. Whereas if the same pedestrian is running towards you, you'd pay attention to him, and he's very important to you. So our hypothesis is that humans attend only to a subset of their surrounding agents while navigating through dense crowds, and this subset is not just dependent on proximity. It's also dependent on higher level features like velocity, acceleration, heading, etc. So we need to account not just the pedestrians who are in our proximity, but also all the pedestrians in our vicinity. In this work, we model the crowd dynamics using spatio-temporal graphs. So these are graphical models where each node represents the pedestrian and the estimated position of the pedestrian at each time step. The temporal edges connect the same node across consecutive time steps and captures the dynamics of trajectories over time. The spatial edges capture different nodes at the same time step and captures the spatial human-human interactions. Now, this graphical model can be converted into a factor graph. And in our work, we use a structural-RNN architecture where each factor is represented using an RNN. So for each node, you have a node factor, which corresponds to a node RNN. And each edge has an edge factor, which corresponds to an edge RNN. In this work, we have two kinds of RNNs, two kinds of edge RNNs, which are temporal edge RNNs and spatial edge RNNs. We'll look more closely into what the inputs to each of these RNNs are. Let's start out with the temporal edge RNN. The input to the temporal edge RNN is the displacement that the corresponding node takes across consecutive time steps. So in this so this can be written as like the difference in XY positions across successive time steps. And this encodes the distance traveled, the velocity, and the heading of the pedestrian. The input to the spatial edge RNN is the displacement between positions of different agents at the same time step. Now, this encodes the distance between the pedestrians and the relative heading. The input to the node RNN is your current time step, is your position at the current time step, and the output of the entire model is the position predicted for each pedestrian at the next time step. To sum it up, you have the inputs to the node RNNs being the current position, the inputs to the temporal edge RNNs being the displacement that the node takes across successive time steps, and the input to the spatial edge RNNs being this displacement between pedestrians at the same time step. Now, our contribution was this attention module, which combines the output of the spatial edge RNNs and feeds it into the node RNN. So to get into more specifics, the attention module predicts a soft distribution over all the spatial edges that go into a node and captures the relative importance of each of the surrounding pedestrian in a crowd. So the hope is that the attention module would predict which surrounding pedestrians are important for you and disregard pedestrians who are not important. So let's look at some of the experiments. So the setup for our quantitative evaluation experiments are that we observe the first 3.2 seconds of each pedestrian's trajectory and predict the next 4.8 seconds. The metric that we use is average displacement error, which is simply the mean Euclidean distance error over predicted time steps. So the predicted 12 time steps, you just compute the mean Euclidean error. We evaluate our approach against social LSTM and LSTM on 5 publicly available crowd data sets. As you can clearly see, our approach has a better error than the baselines, lower error. But more importantly, what we set out to do was to understand what the model learned. So we try to analyze the behaviors captured by the model by observing what it pays attention to. So in the following slide, you would be seeing a lot of these figures, in which the red trajectory represents the pedestrian whose attention weights we are predicting. The rest of the trajectories are the surrounding pedestrians in the crowd. The blue dot denotes their current position, and the radius of the circle is proportional to the attention weight. So the bigger the circle, the more important the pedestrian is. So let's look at some qualitative results. So in this, we present 2 scenarios where in the left scenario, you can see that our model learns to ignore stationary pedestrians irrespective of their proximity and pay attention to pedestrians who are moving. So this makes intuitive sense. You wouldn't pay attention to someone who is standing nearby, but you would pay attention to someone who is moving and could probably be in collision with you in the future. In the right, you see a scenario where our model pays more attention to pedestrians who are moving in the same direction and pays less attention to pedestrians moving in the opposite direction. This also makes sense because the pedestrians moving in the same direction might be in future collision with us. We look at some more scenarios. The scenario on the left, you can see that the pedestrian the model learns to give attention to pedestrians who are moving in the same direction and could possibly in future collision, and ignores stationary pedestrians and pedestrians who are moving in the opposite direction to your back. And in the right, you see the extreme scenario where every pedestrian is really far away from you, and you give equal importance to all of them. So to conclude, we propose social attention. This is an algorithm for accurate trajectory prediction that can be used for safe and interpretable robot navigation in human crowds. But more importantly, the trajectory predictions are explainable, and most of the common behaviors that we exhibit in crowd navigation are captured by the model. Our software has been shared, including the baselines on GitHub, and future work includes accounting for static obstacles in the scene. Right now, our work doesn't account for static obstacles, but it's very useful in robot navigation. Another future work is to actually deploy this on a real robot and have it operating in real dense human crowds. A more interesting work is to come up with a better evaluation metric for evaluating whether a resulting robot trajectory is human-like or not. Right now, we have used a very simplistic error metric like average displacement error, but future work, a potential future work could include coming up with a better evaluation metric. Thank you.
So any questions or comments? Hi, great presentation. I'm curious if you have given any thought for future work, possibly in terms of you look at human-human interaction, and now you're looking at human-robot interaction. Have you looked at the inverse, like what the human interaction will end up looking like when they're seeing robots coming at them?
Yes, I think we definitely did give a thought into this. I think humans don't perceive robots the same way as they perceive other humans. I think a way to actually capture this is to record data with an actual robot operating in human crowds. We need not have an autonomous robot. We could just teleoperate the robot and see how humans react to that and actually model that interaction too. It's definitely an important step towards social robot navigation. I agree.
So any other question? I have one quick question. Interesting to see the pattern that is important to give attention. But you found only one that is that the pedestrians working in the same direction is given high attention, or are there any other patterns that emerges from training?
Yeah, if you look at the paper, and there are more results in the paper where you can see that you pay attention to pedestrians who are moving at a higher velocity than pedestrians who are moving at a lower velocity. I think the major outcome of this work was that proximity is not the only indicator. And all the previous works in this area have looked at just spatially local interactions, whereas interactions can be like spatially far away too.
Okay. So any question? All right, let's thank the speaker.